The purpose of this unit is to stitch together some of the reaction types that we've learned about in the last several units in order to look at how we can go about multi-step syntheses to yield alkyne reaction products. And this is a very applied unit that is very, very applicable to the real world, because typically in the real world, if you're working in an organic synthesis lab, you're carrying out multi-step syntheses aimed at a particular targeted final product, a product that could be useful as a consumer product or a drug or something that has a lot more value to society than the starting materials that you're working with. So you're looking at how can you string together one reaction after another in order to yield a final complex molecule out of a simple starting material. So what we're going to do is look at an example problem and illustrate some strategies that we can use to think about how to make complex molecules out of simpler starting materials. Let's go ahead and get started with that. So in this problem, what we will tackle is we're going to try to synthesize the alkene molecule listed below using only organic reactants that have 2 or fewer carbon atoms. In other words, what we're saying is that your lab is stocked only with molecules that have 2 or fewer carbons. You don't have access to anything more complicated than that to get started, except that you do have access to any inorganic reagents that you need. So the way that we will think about this is by using a technique that we refer to as retrosynthesis. Retro meaning backwards. So when we think about retrosynthesis or retrosynthetic analysis, what we are thinking about is how can we work backwards from the target back to starting materials that would allow us to create this target. So rather than looking from reactant toward product, which is what we've been doing typically up until this point, we're taking a target and we're thinking backwards to what reactants can we use to create that step by step. So we ask ourselves in one step, what can we do to create this alkene out of a couple of starting materials? And when we think about this, we also need to think in the context of somehow we're going to have to create new carbon-carbon bonds because we're only allowed molecules to start with have 2 or fewer carbons. And our final product obviously has 4 carbons. So we need to make a new carbon-carbon bond along the way, which makes me think that at some point we will need to do a carbon-carbon bond formation reaction. The only one we really know at this point that I can think of offhand is taking a deprotonated alkyne nucleophile and reacting it with an electrophilic carbon. And that's certainly a way we know to make a molecule that has greater than 2 carbons. So when I think about this alkene target, what I want to think about is what alkyne could we use as a precursor to that? Because if we can use a 4-carbon alkyne as a precursor to that, we can maybe figure out how we can make that 4-carbon alkyne using 2-carbon precursors to that. So we could think about this, and if we start with looking one step backward from the final product, a 4-carbon alkyne, to convert that into a 4-carbon alkene, we know a couple of routes to do that. One is that we could use H2 with Lindlar's catalyst. That was that stereoselective Sen addition to give us an alkene product out of an alkyne starting material. That would be perfectly acceptable here. Or we could use ammonia with sodium metal, which was another way that we talked about the anti-stereoselective process we talked about for converting an alkyne into an alkene. So we've got that part of the process nailed down here, possibly. A common thing with these is that you will sometimes realize that you've led yourself into a corner and you have to back up and think about what other ways you know to do the reactions you desire. So thinking it now one step further back, do we know of any way that we could create a 4-carbon alkyne out of maybe something that has fewer than 4 carbons? And the way that I can think of to do that offhand is if we can make a carb anion available, for example, something like this, reacted with a molecule that has a leaving group bonded to it that's a 2-carbon chain. So something like ethyl chloride, for example. We could have our lone pair electrons from the carbon come over, attack that carbon that's bonded to the leaving group breaks away. And no, the question doesn't ask for a mechanism. I'm just doing this to help myself stay organized about what I'm plugging together here. That would give us a 2-carbon chain right here from the red carbon atoms. And then the 2 blue carbon atoms would be these 2 guys right here, connected by the new covalent bond that we show in green. So here, going back to this step, what we've shown is that we can take to 2-carbon precursors, and we can react those to give us our desired alkyne. And then keeping in mind that the deprotonated alkyne is not something that you could actually go out to the store and purchase. It's highly unstable, so we need to create that in our lab as well. And the way that we do that is by taking the protonated standard alkyne. This is called acetylene, or also known as ethyne. And we could take that ethyne and deprotonate it. So I'm just going to show that bond explicitly there using, for instance, sodium hydride in a plus H minus as our base to grab that proton from our acid, forcing the carbon-hydrogen bond to break like so. And that would allow us to create our deprotonated alkyne product that we see there in blue. So this is going to be a complete pathway to allow us to synthesize the molecule shown here, our final target, that is alkene, starting in our lab only with molecules that have 2 or fewer carbon atoms, and then using any inorganic reagents that are needed along the way. And the technique we've used to accomplish this is called retrosynthesis. It's where we're thinking backwards, one step at a time, to ask what reagents could we in one step use to complete each reaction along the way, working backwards to get back to final starting materials that are simple enough that we have access to them in our laboratory. We'll then try another example problem here, where we're asked again to propose a route to synthesize the molecule shown below, using only starting materials that have 2 or fewer carbons and any organic reagents that we need along the way. So let's look at how we would go about making this molecule. You're encouraged to hit pause and see if you can come up with a route. And I will mention here that when we talk about synthesis, oftentimes there's more than one correct way to get to the same final product. So just because you don't come up with a synthesis that's identical to the one I've proposed doesn't necessarily mean that yours is wrong. And you're always welcome to run these syntheses by me to see if your logic makes sense or not. So we're going to try to get to this target molecule here, and thinking backwards retrosynthetically, we ask, what one reaction could we do to yield this geminal dihalide product? So you have to think back to what reactions do we know that yield geminal dihalide products. And one reaction that I can think of, the only one that I can really think of offhand, is that we can take an alkyne starting material like so, and we can react that alkyne starting material with 2 equivalents of haloacid. So 2 equivalents of HCl in this case. That's going to follow Mark's rule both times to add H to the carbon that is less substituted. So we're going to end up adding 2 additional H's here on the left-hand end of the molecule, which would correspond to right here. That makes sense. And we would then add the 2 chlorines to that carbon atom in the middle, which that makes sense as well. So this reaction, totally valid for taking our alkyne and converting into the geminal dihalide product that we desire. We then, though, have to continue thinking backwards because our problem here says that our starting materials that we begin our pathway with have to have 2 or fewer carbon atoms. And right now, we're looking at something that's 3 carbons as our starting material for this reaction. So looking back another step here, we have to ask, what can we do to make that alkyne? And is there any way that we can make that alkyne from something that has fewer than 3 carbons? Because we need to get back to starting materials ultimately that have 2 or fewer carbons. And that brings us back to thinking about that new way that we learned to make carbon-carbon bonds by taking a deprotonated alkyne, like so, and reacting that with a molecule that has a leaving group. So in this particular reaction, our deprotonated alkyne is right here, which corresponds to these 2 carbon atoms are our final product. And then we have 1 additional carbon atom that we need to plug into the chain right here. So what we'll do to accomplish that is we'll react our deprotonated alkyne with methyl bromide or methyl chloride, whatever we want, something that has a good leaving group bonded there, so that our carb anion can act as our nucleophile, coming in, attacking the molecule as the leaving group bonded to as the leaving group leaves in an SN2 reaction to give us our 3 carbon chain. And then, much like in the last example, we need to take that deprotonated alkyne back 1 step further and create that from something that we can actually obtain and work with, something that's relatively stable. So we can start with the acetylene or ethyne starting material, treat it with a strong base such as lithium diisopropyl amide to give us our deprotonated alkyne there in that acid-base reaction. So now We've worked our way backwards so that all we would need to purchase in order to do this series of reactions are molecules that had 2 or fewer carbon atoms, thereby accomplishing our goal. Now we're going to provide a route for synthesizing the compound that's shown below using only molecules with 2 or fewer carbon atoms as the starting materials and any inorganic reagents that we need. So we take a look at this, and this is a ketone as our final product. You'll also notice that has 5 carbon atoms. The earlier examples had only 4. This problem is going to be likely a bit more challenging than the ones we looked at in the past, but I think you're up for the challenge now. So take a look at our ketone and think about what's one step looking backward that we can use to create a ketone as the final product. And one way to think about this generically to organize your thoughts is think in terms of functional groups. So in other words, what one reaction do we know that will take some starting material and convert it into a ketone? The only reaction we've learned so far this semester to convert something into a ketone is we learned how to convert alkynes into ketones by using either hydroboration oxidation or acid catalyzed hydration. And so let's think about what we could use as our starting material to convert some alkyne into the ketone product that we see here. So our ketone product has a total of 5 carbons. So we need to make sure that our alkyne has 5 carbons. And the way that the location of the alkyne group works out relative to where the ketone ends up is the alkyne group either needs to be going right here or coming this way. It doesn't matter which, since those two are symmetrical. So when we draw out our alkyne starting material with our 5 carbon chain, we need to place the alkyne group between carbons number 3 and 4 of the chain, or between carbons 2 and 3 of the chain, however you want to look at that there. So we'll go ahead and draw this out. And I'm going to go ahead and number the chain to make sure I have my 5 carbons in there. 1, 2, 3, 4, 5. And thinking about whether to do hydroboration oxidation here for this molecule or acid catalyzed hydration, it doesn't really matter which one you do here because of the fact that both of these carbons are equally substituted, which means that they're both going to be susceptible to getting the carbonyl on them. So we could do hydroboration oxidation, which, remember, in order to use this, you have to incorporate borane first, followed by our oxidation with peroxide, and we'll also have sodium hydroxide in there. That would be hydroboration oxidation option, or acid catalyzed hydration, which would be our acids such as sulfuric acid, water, and mercury catalyst, Hg2+. Either of these will work here, and do keep in mind that based on the starting material that we used, we would actually end up not with just this one constitutional isomer product, but we'd actually end up with a second constitutional isomer product as well that would correspond to having the carbonyl group at carbon 2 of the chain instead of carbon 3 of the chain. And that's going to occur because of the fact that we have these 2 equally substituted carbons in our starting materials, and so they are both going to be prone to ending up with the carbonyl group in the final product. And that's okay. At the end of this, what you would do is separate those 2 constitutional isomers by using a chromatography experiment, and you would discard this one right here. Sometimes it's necessary in order to get to the product you want, that you'll have some side products that you're not interested in. So you discard that one at the end using the technique that we are seeing here at taking an alkyne and converting it into a ketone. Since this is the only way we know at this point in the semester of making ketones is taking alkyne starting material. So that's why we looked back one step and used an alkyne as our starting material for this. And then going on backward, because at this point, what we're seeing here is that our alkyne has 5 carbon atoms in it, and we have to start with things that have just 2 or fewer carbon atoms. So we have some work to do to get back to molecules with only 2 or fewer carbon atoms as our starting structure. So to work backward from here, we need to think about what can we do to make a 5 carbon alkyne in one step, and then we'll simplify on down from there. So to make a 5 carbon alkyne in one step, the only way I know to do that, based on what we've learned so far, is to take a deprotonated alkyne and react that deprotonated alkyne with a electrophilic carbon that has a leaving group bonded to it. So in order to accomplish this, what we can think about doing is take, for example, and make a 3 carbon chain here with an alkyne group at the end, because we have to have an alkyne group at the end, in order to enable deprotonation of that alkyne. So we take a 3-carbon alkyne here, and this corresponds to what I've circled in red there. We would treat that deprotonated alkyne with a base, such as lithium diisopropyl amide, to give us the deprotonated alkyne with 3 carbon atoms like so. And then that deprotonated alkyne, we would mix with our molecule that has a leaving group bonded to it, and that molecule with the leaving group bonded to it is going to have to be a 2-carbon chain because we want to make a new bond here between the alkyne group and that carbon of the 2-carbon chain. So we can do CH3, CH2, Cl, or you could also use bromine there, or iodine, or whatever you wanted to use as your leaving group. Carbon anion comes over, attacks that carbon that's bonded to the leaving group as the leaving group leaves in that SN2 type reaction, and that would enable us to generate the intermediate reaction product that's seen right here. So clean this up just a little bit here by doing some erasing. All right, so we're working backwards, going from our ketone, then back another step to taking a deprotonated alkyne and reacting with an electrophile. Back one step again to get back to our 3-carbon alkyne plus our base. And then we still have to work backward a bit more from there because we have a 3-carbon alkyne here that we're using as our starting material, and we need to work backwards until we're only using molecules with 2 or fewer carbons. So we need to think about how we can make this 3-carbon alkyne that I have shown in red here. And the way that we can accomplish that is by doing a nucleophilic substitution reaction. And in that nucleophilic substitution reaction, to get things going here, we'd have to take a 2-carbon alkyne and react it with, first off, a base to generate the deprotonated alkyne product. So we deprotonate one end of that alkyne to give us our carb anion there. And then we take that carb anion, which will be our nucleophile, and react that with an electrophilic carbon. And in this case, our end game here is to get to a 3-carbon product. We start off with a 2-carbon alkyne, so therefore we need 1 more carbon. So therefore we'll do CH3Cl, and we take our carb anion, bring that over to attack the carbon here as the chlorine breaks away, giving us our 3-carbon chain in our product, where our methyl group that we had in blue up top is the methyl group right here that's connected by the new covalent bond that was shown in green. So now that we look back at this, we have indeed shown that we're back to a starting structure that has only 2 carbon atoms. And as we go along, any reagents that we need to purchase along the way would have 2 or fewer carbons. So pretty much the only organic molecules that we need to purchase would be this alkyne that has 2 carbons to start with, the alkyl halide that has the leaving group right here, the ethyl chloride right here we would need to purchase because we didn't show how to make that. And that is it. That's the only 3 organic compounds that we need to purchase along the way in order to do this synthesis. Everything else that's listed here would be things that we would make ourselves in the lab or that we would purchase. So we have indeed shown how we can work using only molecules that have 2 or fewer carbons as starting materials to generate the final 5-carbon product target that we've shown below in this multi-step synthesis. So what we're doing here, again, is we're going step by step by step, showing what reagents we need to mix together in order to accomplish the targeted product in each case. And you'll notice here that I didn't say anything in the materials about show a mechanism for any of these reactions. So what that means is if I ask you this type of question on an exam or something like that, I'm not expecting you to show electron pushing arrows to go from reactant to product. I'm expecting you only to show what reagents you need to mix together and what final product would result from mixing those 2 reagents together. The electron pushing arrows that I've shown here in this are purely optional because they helped me in piecing together what's happening at each step. So I would expect you at this point in the semester to be able to take and apply the reactions that you've learned in this chapter or others to piece together 2 to 3 step, multi-step reactions to allow you to make molecules of moderate complexity, like the ones that we've shown here, that 4 or 5 carbon atoms that we can accomplish in somewhere between, say, 3 and 5 step syntheses. And this is where we really start to determine how well you've mastered the reactions that we've been talking about this semester. We're starting to take some of the training wheels off with regard to reactions and focus more so on actually applying reactions and less on just learning what the products are of individual reactions. Because in the real world, what happens is that you generally have to piece together multiple reactions to get to the destination that you desire. And so it's really important to be able to think backwards from what your final goal is or your target molecule back to how you would start with that. What are the simple building blocks and foundation that you can use to make a final product that is really complex? That is super important and really the crux of a lot of accomplishments in organic chemistry.